I'm super stoked to be here and present to you Collide+Power. This was a long work with a lot of collaborators in a way, but I'm happy to be here and present it to you. So let's start over with a bit of motivation why we think that Collide+Power is a game changer in the area of software-based power measurements. So we have seen in the recent years that there are much more software-based power side channels emerging in the past. We have seen Platypus and also more recently the hard split attack. Those software-based power side channels usually have in common that they target a specific algorithm. So they abuse, for instance, the structure of the AES instruction set in their attacks. For example, there are a lot of attacks that exploit some edge cases. Think about like some edge values. For example, in areas A, square and multiply, I can distinguish if-else branches. Also, Psych had this interesting problem with a certain edge case in the implementation, and this was even exploitable in the hard split paper over a remote timing side channel, basically. Also, like all these attacks work with KSLR, where you have edge cases between mapped and unmapped memory. And those works are basically limited to a side channel. They are side channel attacks. These can be applied to some targets, but they exploit these edge cases. And on the other side, we have these transient execution attacks. And these attacks are more on the generic side of attacks. For example, they target CPU components. They don't care as much about the structure of a program or algorithm. They're more targeting to leak data from, for example, the cache or internal buffers. So we see here a clear distinction that these attacks are not targeting edge values, but more precisely, they're more like arbitrary data leakage primitives, which give you back the precise data. And with Collide+Power, we try to combine those two fields and create a technique or a framework to basically build an arbitrary leakage primitive with any side channel to use. For instance, MDS and Meltdown, they are side channel agnostic since the side channel is exchangeable. And this is the aim of Collide+Power. So first of all, we have to get on the same page. So I will spend a lot of time of like just providing a high-level intuition what we're actually doing. So power side channels are not new. They are super old and they have some applied techniques in the past. For example, we usually build power models, and classical components of power models are, for example, the Hamming weight. And the Hamming weight is a single input function which basically models the number of bits set in a word. For example, if we have the Hamming weight of 3, here in binary, we have 2 set bits, so the Hamming weight is just 2. On the other side, we also have like the Hamming distance, and this is a 2-input parameter function, and this is super useful because we built a hardware in a certain way. The Hamming distance can model basically the transition from one value in that hardware component to another value by modeling the difference between 2 data words. For example, if we have the Hamming distance between 3 and 1, we need to change exactly 1 bit to transition from a 3 in binary to a 1 in binary. And now Collide+Power builds on this Hamming distance leakage. So we exploit leakage between an attacker-controlled guess. So think about our threat model assumes that the attacker has some data, some user data, which we can change. And we target a victim value V, which is basically the secret data of our attack. And now we abuse in the power model, if we find a component in a CPU that exposes this Hamming distance between the attacker-controlled data and the constant victim value V or the attack. But you might be wondering, the Hamming distance just tells us a bit difference. How can we actually exploit this bit difference to get like the real data out of it? And therefore, we will now make an intuitive example with a really simplified power model. For example, just the Hamming distance. And we can summarize again. So basically, we have here a power model. This is reflecting the actual hardware consumption, the energy consumption of the hardware, and the signal which we try to exploit. And in our threat model, we now try to leak this victim value V, which we now assume in this example to be 5. And the attacker has control over the guess. So what the attacker can now do is just do binary guesses. For example, if we now replace our attacker-controlled data with the binary value 8, and the hardware exposes the Hamming distance between those 2 values, we will see an increased power consumption. If we now try a different bit, and we have the Hamming distance leakage between, and the bit is set, we need to change less bits during the transition. This means we reduce the power consumption, And we can see this in our power measurement. And if we continue for all possible bit positions, we can see that in the diagram, we leak the inverse bit pattern of the victim value V. So this is just a high-level intuition example how we can exploit the Hamming distance. In the paper, we use a much more sophisticated and statistical approach. This correlation power analysis is also known for a long time. And yeah, we build on top of that in Collide+Power. So you might be wondering, this is now super abstract and it's like a high-level example. So where do we find Hamming distance leakage in a CPU? And the good or bad answer, depending on from whom you look, is basically nearly everywhere. Every time we have a shared component, we observe some sort of Hamming distance leakage. And you might have seen some similar diagrams in the past 2 days. We target, for example, the cache. And what the cache basically is a shared resource which different security domains and is usually constructed in sets and a number of ways. And what the attacker can now do is basically fill one set of the cache with this guess, attacker-controlled guess, and wait or force the victim to, at some point, override one of those attacker-controlled guesses. And in order to override data in the cache, the data has to come from somewhere. So basically, the data is traveling over the internal buses until it ends up in the CPU cache. And that's exactly where we can exploit and observe this Hamming distance leakage between the attacker-controlled guess and this victim value. So you might be now screaming at the screen and saying this looks like prime and probe. And you're right, this is the same pattern as in prime and probe, but we have a few small nuances. First of all, we don't care about access patterns. The thing we leak, we assume it's constant time, or constant cycle at least, and we are not interested in leaking access patterns. And also in this variant, in Collide+Power, we care about the precise value of the eviction set. So since we targeting cache, we also need to analyze it. So we assume that there's leakage in the cache, but how can we find it and how can we test it? So in order to do the leakage analysis, we basically build an eviction set, which is generic for L1 and L2. Therefore, we use 16 distinct cache lines, where 15 of the cache lines are the attacker-controlled data, so the 15 cache lines of the attacker, and we target one cache line of the victim. And during this initial leakage analysis, we basically iterate over all the cache lines and just access them or prefetch them into the memory. During the experiments, these cache lines are located in different positions in the L1 and also in the L2. And on the side, we record basically which parts of the cache line leak to each other. This means if we split the cache line of the guesses and the cache line of the victim into 8 equal-sized parts, we will see leakage between those different blocks. For example, if we simply place each of those cache lines in an individual L1 set and L2 set, we don't have any eviction happening on the system. But still, due to the loads, we observed that already on the top left corner, you see that the lower part of the cache line of the guess is leaking to the lower part of the cache line of the victim. And it only gets more convoluted if we add L1 eviction, for example. If we now place all the cache lines in the same L1 set, we will see that this diagonal is appearing. And even if we go one level further, if we also evict from the L2 by placing some of the cache lines in the same L2 set, we get additional leakage components in this power domain. This is the most generic analysis we can do, but it's super slow. So we can use the insights we gained to abstract away and define 3 types of leakage. First, we see aligned leakage. This is basically the leakage between cache lines aligned to each byte or each bit, basically. We also see cross leakage in 32-bit blocks because of bus width changes between the L2 and the higher levels of the cache. And finally, we see also interesting effects due to those bus width changes that we leak our own data. It's called self-leakage, where we leak the upper part of our cache line to the lower part. In the paper, there are a lot of tables which go in detail over what we actually analyze and to quantify the leakage. Don't read this table, it's super large. I just want to highlight one particular number of this table, and it's basically the correlation of our model when we consider L1 eviction. And we reach a correlation of 0.9 for this energy domain. So this means our model is super accurate under the case of constant L1 eviction. So what can we do with this? we can go back to the beginning of this talk and now build these generic attack primitives we wanted to have in the first place. We can build an MDS-style attack, and we use the same threat model as like MDS-style attacks do. We assume that we have an attacker that constantly accesses its own guess on a hyperthread. And the victim is also constantly accessing its own data. And due to these accesses, like we've seen in the no eviction case, we already get collisions on the bus. And these collisions we can exploit and leak the data from. Also, we can build a Meltdown-style attack, which is basically removing the requirement for hyperthreading by doing, like we've seen in the L2 eviction case, we prime our cache set, and then we use a Spectre gadget in the kernel to load arbitrary data, for example, the victim data, into the cache and force an eviction. Here we can see that the data is colliding in the buses and in the caches. And you might be wondering, okay, we're now combining software-based power measurements with Spectre prefetch gadgets in the kernel, miles away from the actual code. So this must be slow. No, actually, it's extremely slow. So we evaluated this because we wanted to have something agnostic to power side channels. So what we did is basically we used the power measurement interface using Platypus, which is basically like giving you the direct energy value. And back then it was an unprivileged interface. This is now fixed, so this is just for reference. An unprivileged attacker doesn't have access to this interface. But hard split, on the other hand, is an indirect power measurement, which is based on frequency throttling. I won't go into details, please check out the paper. So we evaluated both attacks, and with the direct energy measurements, our MDS-style attack leaks around 4 bits per hour. Our Meltdown-style attack with the RSP gadget leaks 1 bit per hour approximately. And if we go to hard split, it gets even worse. So based on which hard split method we use, we leak like nearly 1 bit per hour. And we only have estimates for the Meltdown-style attacks because it took way too long. So we estimate to leak either 1 bit per 100 days or 1 bit per 2 years. So these are just estimates, we did not try this. And to conclude, Collide+Power is a generic arbitrary data leakage primitive that can escalate arbitrary power-related signals to a generic primitive, and it's super hard to prevent data collisions in shared resources. I'm happy to announce that we passed the artifact evaluation, and for more details about like how do prefetches involve this and how can we amplify the signal, please refer to the paper. Thank you.